Hello, everyone. Hope you are all staying safe and warm. Welcome to seminar number 3 of our virtual architectural seminar series. We have been providing architects with these valuable educational opportunities for over 30 years, and we are pleased that you're able to join us and continue to find a safe way to provide this value-added service. My name is Vicki Strand. I'm your Director of Marketing and Communications for Construction Supply Group. We are excited to begin our integration with our Construction Supply Group businesses and Whitecap. We are combining to better serve you. Our mutual commitment remains to being better together and building trust on every job by providing you with exceptional service and knowledge of the industry. As a reminder, today's presentation is an AIA-approved 1-hour, 1 HSW credit event. Today, we will learn about Nudura Insulated Concrete Forms. They will talk about educational buildings. We will review the basics taught in the Introduction to Insulated Concrete Forms, but focus on the use of ICF technology for its benefits and advantages in terms of application to educational facilities. Before we get the webinar started today, I would like to go over a few items so you know how to participate in our event today. We do have everyone muted as to eliminate any noise and distraction. We've taken a screenshot as an example of the attendee interface. You should see something that looks like this on your own desktop computer in the upper right corner. When you joined today's call, you selected to join by phone call or computer audio. If for any reason you would like to change your selection, you can do so by changing your audio control in your control panel. You will have the opportunity to submit text questions to our presenter today by typing your questions into the questions pane of the control panel. You may send in your questions at any time. We will collect them and address them during the Q&A session at the end of today's presentation. Today's presenter is from Nudura is Justice Olson. Justice joins us from southwestern Wisconsin and has been in the construction industry since 1997. In his current role, Justice is a senior technical sales representative. Justice believes that being exceptionally thorough on the front end results in a more cohesive team approach, creates expectations, trust, and reduces risk for all involved. Justice has dedicated the last 17 years to continually improving the design and construction process in the ICF industry. Combining his knowledge of residential and commercial construction, ICF installation, estimating, project management, Justice's commitment to promoting and educating architects, engineers, and installers has resulted in successful projects throughout North America. These projects range from your basic residential home, large commercial and military projects, and most recently, completing the first net zero school on tribal land in North America. Justice, thank you for your time today. Are you ready to start today's presentation?
Well, good afternoon. Thank you, Vicki. We'll get started today. This is an AIA, and we are a registered provider. And I'm trying to get my slides to click here. So as an overview, this is really a complete overview, kind of a 30,000-foot view. We're not really going to dial into the specifics, but we want you to understand what an ICF is, or an insulated concrete form, the different types of ICFs, the benefits of building with ICF, construction process. We're going to actually kind of get into some building types, or better yet, some actual projects that we've done for educational facilities, codes, and green. If anybody is designing with LEED, we'll touch that as well. So I did this presentation 2 years ago with Stetson. It was an introduction to insulated concrete forms. Now this is kind of a second step. But just as a complete overview, insulated concrete forms, what are they? They are a stay-in-place form. Most of the systems today are made out of expanded polystyrene, or EPS insulation. You have 2 panels that are held together with engineered cross ties or webs, and they're going to actually hold that form unit together during the concrete placement and consolidation. The systems out there do allow for rebar placement inside that web and tie assembly, and then at the end of the day, you have a final product that is a reinforced concrete monolithic wall. Just a little brief history. The first ICF done in North America was 1961. We've come a long way since then. First generation would have been your post and beam. That's that center photo. Second generation ICF would have been the waffle or screen grid. What that is it's just a post and beam that has about a 4-inch core in between the post and beams to add strength for, I would say, soil conditions. But again, that's where the flat ICF came in to resist all those pressures, then below grade and above grade. So 95% of that market today is that flat wall ICF. And that'll give you a common core thickness of about 4, 6, 8, 10, and 12. Those are your standard core thicknesses through the industry. The form on the left is, again, a generation 2 or 3 for the ICF world. And it's a module unit that is completely assembled, but comes to you just as you see in the picture. It doesn't collapse. So it does add a lot of air in a trailer as it comes through on square footage wise. The third and fourth generation would be a system that does fold, and there is only a few out there that do fold, but everybody has pretty much the capability to do site assembled, and that's an unassembled series to where you would install that in the field or put together in the field. And where you might see this is when we get into heavy rebar congestion, unique applications to where you want to maybe work on that cage of rebar. You can now put on that outside skin, put the webs in, and then the inside panel. It gives you that unique ability. But most importantly, most of the systems out there are going to ship to you site assembled. So, you know, a couple benefits of building with ICFs are you've heard it before, energy efficiency. But some of the outliers there are really more important than just energy to some ownership groups. Fire resistance is important. Sound attenuation or sound resistance. Storm resistance is playing a big role. As you start to design any educational facility, I believe Iowa, Missouri, you know, states like that are going to have that ICC 500 requirement. And we do meet the standards within that for storm shelters, whether that's a gymnasium or converting a locker room into that, just having a place to go to. It integrates well with the ICF and the rest of the building. So indoor air quality, think of air infiltration. Yeah, I don't have any bad air quality coming inside the building because it's really not going to go through concrete. And of course, speed of construction. And so when we break this down on energy and air infiltration, think of the wall as a heat sink, or yeah, it's thermal mass, so it's going to have a heat sink. We are just an R24 on paper, and what that is, it's an R23 for the ICF form. Every ICF form out there uses a type 2 EPS. Type 2 EPS as an R value is 4.1 per inch. So most of them are between 22 and 24 inches. Or sorry, R value, 22 to 24. You have probably seen this statement in the past, perform to an R50. We are not an R50. What that is saying is if you wanted another wall assembly, like a cavity wall, to perform at the same rate as an ICF wall, you would almost have to put that at an R48 to an R50 to get the same performance. Airtight envelopes. When we think of the 6 sides of that wall, walls, roof, and slab, we now know that there's energy lost in all points of that. So we want to start at that envelope, and this is a great way to address, you know, that first cost or that first input, and then we'll tie in some roof assemblies, you know, insulate that slab, throw on some air barriers, some WRBs, and now we're starting to really address all of those components there. Fire resistance, our 4-inch core starts at a 2-hour fire rating. Our 6-inch core is the same as our 8, 10, and 12, and that'll get you your 4-hour fire rating. We do have a UL listing. That, you know, is probably the gold standard, but it does address ASTM E119. Again, most projects on the commercial side are going to start out at your 6. Most after that are going to be your 8-inch, and you are going to be set with a 4-hour fire rating. When we think of STC or sound barrier transmission, I know the photo here shows a theater, which is a great application, but as we start to teach in classrooms, maybe not this year, but we will get back to the classroom. You know, we are going to have classrooms stacked upon each other, and sometimes we get that transmission of sound, and it maybe is disruptive to other classrooms at times. Think of auditoriums, gymnasiums, all of the commotion and the sound that comes in and out of that. So an effective sound barrier as well. Your 6-inch core is going to start out, I think, at a 52 STC. You can achieve up to that 68 to 71 as you go through there. Again, you're putting, you know, other systems on top of that, some claddings, thermal barriers. For us, you know, this is a side of the concrete wall that we're proud of. It's the storm resistance or wind resistance, whether that might be a tornado or a hurricane. Mexico Beach about a year and a half ago, I think everybody has seen that house standing there on all of those piers. You know, that took a direct hit. And about 30 miles west of that was a school that you'll see here in the photos that was in that tornado, was under construction, just about finished, but no damage whatsoever. So again, as we think about that, what are we trying to protect? Not only in homes, but in our day-to-day lives at school. So mold resistance, you know, allergens, they still play a part. You know, kids come to school, you have video peanut allergies and mold, things like that. So what we're trying to do is to let you know that plastic insulation does not have a food source. Concrete does not have a food source. The mold resistance is fantastic because there is no food source to support mold growth. Speed of construction, you know, as we think about this and we take an educational facility that might last 12 to 18 months in that build schedule, we're all from the Midwest, right? So we know winter does happen here. This type of construction does not need to be tented. We can work in the conditions. We don't need to be heated. As long as we can make concrete, we can pour concrete. So it's as simple as tenting the top of that wall or the window openings so that they don't freeze before the concrete cures. But speed of construction, extended building season, they all really play a part in our budget as well, not just in speed, but winter conditions, they impact the cost of construction. So as we start to look at what are ICFs, you know, it's more than just insulation. I got something going on here. Hang on one second. Let me get back to this here. It's simplicity of design for the architect. It's what am I designing with? What do I have to put over top of this? What's got to be in that wall assembly? Can I reduce it? And sometimes, you know, if we look at the green aspect, it's maybe not what you put in a building that makes it green. It's what you can take out if we're looking at it from that scope. If we look at it from a risk scope, you know, the design team, the ownership group, you know, how many components are going to be layered in that wall and who's responsible? Will they interface with product warranties on the backside? When you have ICS, we might be able to take that wall component from 9 or 10 layers down to 3 or 4 layers. So it takes away risk. Its simplicity of design is all integrated assemblies. You know, we have the concrete, we have the reinforcement, we have the air barriers, we have the web and tie assembly for furring and structural support during that head pressure pour. So when we walk away from that, we have far less warranties to worry about. We have fewer fingers to point in case something does happen. So what I'll do now is I have a short little video here for you. There is no sound, so if you don't hear anything, it's not intended that you should be hearing something. And I'll kind of just point out a few things as we go through here. Here he's simply just creating a whaler or a batter board on the footing to help support that to get started. And he's just going to screw that off to the block. Here he's literally just stacking the forms in place, and at this he'll start to lay out window and doors. You know, they're going to come in off of the footing height or stem wall or frost wall. And here he's starting to come around. That's a Stala integrated frame assembly. It's a window bucking material. And we'll talk about that as we get into window and door bucks as well. Simple reinforcement, he's using a C-clip. He's going to have vertical steel, creating a pattern here around a window opening or a door opening. You know, as you look at this scaffolding system, this is a safety rail system. It is a way to work off that platform, provide safety rail. It's going to move your wall in or out as you make those adjustments. Here's a faceplate. This is what we might typically do when we integrate red iron steel or anything that might interface with that wall assembly. This is probably the quickest way and simplest, is cut out that foam, get some Nelson studs on a faceplate, and pour flush to the UPS. Here they're placing concrete. They are internally vibrating. You're going to vibrate internally and externally. It's concrete. It needs to get that air out of there, and it's going to help consolidate around all of that rebar. Face plates, weld plates, you know, these are just embeds that are going to carry a steel or a decking system, much like you might see here. So it's just bucked out. They put in that heel and then they weld it. Here they're putting on a flashing for some brick veneer, and now you start to work on the inside with electrical. You know, it's just your gang form box, some conduit. You're going to create chases like you see at the bottom of the wall. I would like to see that foamed in actually. Once you create that chase and put in your conduit, you should go back and foam that in and get rid of that cavity in the wall. So again, a real quick video. It was just intended to, you know, kind of bring things to the forefront or bring things to the light. You know, and now we'll kind of go through the process. It's just like any other building method, people. You're going to start with a footing, and it's going to be formed. It's going to be based on soil conditions, weight of wall. But again, you're going to start on that footing, and you're going to start stacking that wall. Here would be an example of a frost wall or a stem wall coming out of the ground. You can see in that picture, they're going to put sleeves through the ICF. You know, as we start thinking about that, we now got to think about waterproofing and how do we terminate around those penetrations, things like that. Again, there's course two. It's typically when you start seeing rebar. We'll start reinforcing, and in this case, they have rebar each face of the wall, both vertically and horizontally. Very easy to do. You'll see those nubs inside that wall assembly. That's the spacing of rebar. So if you take it the leftmost or the outermost positioning bracket, you're still going to have the required concrete around that rebar before you interface with the EPS. The photo on the right is a view looking down on top of a head or a window or door detail. You'll see the stirrups there, the box stirrups. They're going to be 8 inches on center. You're going to have a bottom bar rebar above that window and a top bar connected together. Again, and then you'll start to see the rebar and how we come out of that window head height. So, and again, is attached sitting in the web and tie assembly. And a number 4 and number 5 bar does not need to be tied off. That capture lug will hold it in place. If you get into some heavy bar calculations, say 7 bar, 8 bar, you're going to need to tie it off. That's just the nature of the beast, but that will receive 4 and 5 bar and not require a tie-in. So you'll see the one here. Again, this is an unassembled series, so we're showing you that even with the unassembled, you're going to have the rebar connectors or the lugs in there as well. It's going to provide you the accurate position of the steel. And there, if we get into something very, very specific to where you've got to have positive bar placement, we do have products to help support that all the way up in a channel. So if there is that question, yes, we could address it as well. Moisture resistance, damp proofing, or waterproofing. Here would be an example of peel and stick. You can also put on a water-based waterproofing, and when you do that, you should also have a drainage mat over top of that. So think of a tough and dry, a Watchdog product. That's probably best going to go over EPS. Notice that the top of that core bowl, they've got a parge coat, and that's going to actually parge off over top of our waterproofing to create and still maintain a drainage assembly there. So this way we can keep all the moisture outside of that waterproofing. You'll see the clear stone down below. You know, eventually that'll have a clear stone pattern all the way up through. So it's really no different. It's just a rolled rubber asphaltic membrane. Again, you can have fluid applied barriers as well. They do work phenomenal. As we start to look into door and window box assembly, you know, it's different than residential construction. You know, we're trying to tie everything back to that concrete. We want to be able to create a hinge side or a door side that's going to have something substantial to lock into. The product on the left is called Pre-Buck. That is specifically designed for ICF, number one, and number two, it's designed to be in direct contact with concrete. You'll see the two fluted barrels in there. That's what locks that buck material into the concrete. And then it actually helps with an air barrier as well. Air is not going to pass through there when that wood either shrinks or the concrete starts to shrink. The second one from the left is going to be just a metal assembly, right? That would be a door. You might see a door like that on a 500 or ICC 500 storm shelter. The bottom middle there, third one from the left, that's a stall of frame. It's an integrated frame assembly. That's used in commercial construction, but a lot of times we do use it in school builds. That's actually designed to work with the ICF, but in the same sense, it actually flashes off, and you can have that set up for a brick veneer return, a stone, a metal panel. There's different channels to think about when you're coming back into that. The top one there is just a different version of a buck and ICF. They have EPS there to help maybe mitigate some thermal bridging risk. But again, it's just a laminated material, and the EPS is what's going to be against the concrete because it's not designed to be in direct contact with concrete. And the bottom right is just your standard ICF wood buck assembly. You still have to have mechanical fasteners when you do this. It's a quick fix, but it's not something that you're going to see a lot of times in commercial construction. Wall bracing, maybe the single most important product on the job site for an ICF guy. This is going to give him the ability to move that wall in and out, to have nice, straight, flat, plumb walls. It's also going to be his safety platform. This is what he's going to work off of as he's starting to erect that wall. It has fall protection on it. He's going to drop that rebar in from the top of the wall. There's going to be a lot of work performed off of this platform. So it should be key. Any installer should have, one, the correct amount of bracing, but two, an OSHA certified scaffolding system. So most large installers might have 200 to 600 sets for that for commercial grade construction. Concrete placement, you know, I'm sure a lot of these questions that you're thinking about just in your head might be, how high can I pour in a day, or what does that look like? So we place that concrete in lifts of about 4 feet. It says 4 inches. I've got to get that switched, but it is 4 feet. That's a rule of thumb. The wetter the concrete or the higher slump, the less height you're going to go. So when you think of 4-foot lifts, you're going to think of about a 5.5 inch slump. It doesn't matter if it's an 8-inch core or 12-inch core, you're still going to go 4 feet. And what we want to do is be able to get back in that amount of time of maybe 30 to 45 minutes from where we started. And what that does is it'll still give you the ability to consolidate lifts 1 and 2, or lifts 3 to 2, or 4 to 3. We want to consolidate that, not have a cold joint. So it's a strategy. Again, 4 foot is the rule of thumb. And it doesn't matter if that's a 4, 6, 8, 10, or 12-inch concrete wall. Completed walls, this is what it might look like if you ever go to a job site when the ICF is complete. They're starting to assemble the roof and interface that with that wall assembly. You can start to see the bucks there, some strapping on the top as they poured through. Again, it's a raw wall. It's starting to come to shape. And, you know, we'll start to look at how do we connect that floor assembly in or that roof assembly in. The top picture is just your hollow core plank that comes in. You'll probably end up pinning that down into the concrete wall, grouting that in. The bottom right is your metal bar truss. You know, that might be spaced 2 foot, 3 foot, 32 inches. It just depends on the span. But you can set that on top of the wall. We can weld it to a weld plate or some like an EcoSpan. You're going to bolt right to the concrete wall. Bottom left, if you're doing multi-family, you might still use a wood floor assembly, but likely we're here to talk about schools. Just know that you can integrate a wood floor deck or a concrete or a metal floor deck. And a roof connection, same rule applies. You know, if you're going to have a parapet that might extend above, we'll just work around that decking heel and continue up, create that separation. Wood truss, you might have some wood truss. It's not likely you're not going to have a combustible material typically, but again, you can insert some anchoring systems. I'm not going to get in to tell you, you know, what's required because that can change by state or even county. But it can be wet set, it can be attached with J-bolts and you know, things like that. So electrical. As we start to work on the inside of this building, you know, we're going to run some chases, and electrical is the most common trade that's going to interface with this wall. Plumbing, not likely. You might have a vent stack through there or just service penetrations, but we can use a wire. I guess that's kind of a box with a wire on it. Heat knife, chainsaws, bottom right. Some use a router. You're going to create channels and you're going to put your conduit in, attached likely right to the concrete, and you're going to foam that back in so that we don't have any air gaps between the drywall and the concrete. We want to fill that back in. Again, plumbing, likely not going to have plumbing on an outside wall. You may have a vent stack. You have about 2 5/8 inches there to work with. You will definitely likely put sleeves in a wall just to get in utilities or venting or intakes. That's definitely a service penetration. You did see that on the slide when we were coming off the footing. I did point that out. Interior finishes. The most economical, obviously, is probably a drywall. In schools, we use a higher density drywall, a type X, 5/8. You're going to return that like you would with cavity or deep wall systems. Still most cost effective. There are some pargings out there that can be parged right on top of the ICF with a mesh. Again, that's, you know, you're getting into a more specific trade, and it is likely more expensive. So when we think about this building's complete, how do I want it to look? What can I put on the exterior of this building? And this here is a hospital, but it's here to show you that you can put anything on there. If you wanted architectural metal panels, you can put it on. Cement board, you can put it on. Most ICF manufacturers have a screw pull test for a number 6 screw up to a number 12 screw, whether that's a metal screw or a wood screw. They each have their own pull-out rating. So as we start to think about what this cladding system is going to look like, we've got to think about what's the capability there. If you have brick 2 or 3 stories, we have tie keys that get cast in with the concrete as it's being poured. So again, stone, brick, veneer, eaves, it doesn't really matter. It's whatever you want that building to look like, and it can be accommodated with ICFs. As we start to get into some of these project profiles, again, I just want to paraphrase that if you were to take every school in America, the average school size is about 72,000 square feet of floor space. The average school in America consumes 74 kBTUs per square foot per year. So if we take that as an average, that's our index. And as we start to go through here, you'll see net zero schools, you'll see schools that are just built with ICFs. We'll try to point out their EUI or energy use index. So here is the Richardsville Elementary School. It is one of the most energy efficient schools in North America. It sits in Bowling Green, Kentucky. 72,000 square foot, came in at a cost of $206 a square foot with the solar panels on top. It consumes 18.9 kBTUs per square foot per year. This annual savings to this district for this school is $223,000 a year. That pays for a lot of books and computers, things like that. Oddly enough, that school also does not have a computer lab. Everything is wireless, and they can take any empty room in this building and create a computer lab based on, hour 1 through hour 8. Beaver Creek is up in Ohio. It's 265,000 square foot. The cost to build was $166 a square foot. Really, really cheap in terms of construction costs, I believe. ICF installation was 6 months. It's 150,000 square foot of ICF wall. So SHP was the architect. It was completed in 2013. Here's another net zero. It's the Locust Trace Science Campus in Lexington, Kentucky. 48,000 square foot, smaller building. It came in at a completed cost of $230 a square foot. It's completed in 2011. I look at these schools and you couldn't tell that it was ICF construction. Some people believe that when you build with just concrete, raw concrete, they're big, boxy, and ugly looking buildings, and that couldn't be further from the truth. Here's a school in Kentucky or Connecticut. 9 weeks of installation time. It's just 19,000 square foot of ICF wall. So average size school, 52,000 square foot. Kind of looks like a house, and not a lot of people can really pull out that it's a school. When we get into the Department of Defense, we start looking at military barracks and the school campuses that are going to be here. Here's Barclay in Fort Campbell. Again, it's 131,000 square foot, but even military standards, it came in at $243 a square foot. It was platinum LEED, and it was completed in 2017. Polbrook is in Fort Bragg, North Carolina. Again, Department of Defense education buildings, $294 a square foot. Capacity is 625 students. LEED silver, and completed in 2017. 2-story facility, a lot of glass on there, a lot of glazing. Again, a nice looking facility. Talawanda is in Ohio as well. This is a larger school at about almost 200,000 square foot. The cost of construction, again, $221. Being from Wisconsin, historically, I hear cost of construction falls in about $250 to $300 a square foot. These schools that are reducing energy and building with ICFs and have all of those attributes are still landing within that budget. So when people think about ICFs, they sometimes think it's expensive, or they heard it's expensive. When we start to get in on the front side of this during the design, we save a lot of those first cost expenses. We just start to transition that, and it usually is just as competitive with CMU or steel stud and red iron steel. Joseph Warren, 300,000 square foot, platinum certified, completed in 2011. This is a very large campus. This one came in at $165 a square foot. Dunes down in Florida, 150,000 square foot of space, 1,000 students, $240 a square foot. Again, LEED certified, I think is what this came in at. So Escanaba, you heard me mention the Mexico Beach House. I gotta, hang on one second. My phone is going nuts. I'm going to shut this off. Cost of construction is 157. This school was 30 miles from the Mexico Beach, which was wiped out by a hurricane. I'm trying to shut my phone off and it's not working. So sorry about that, guys. Again, this was finished it started in January. And I think by the time they were done with all the ICF, it was first part of June. So in 6 months' time, they erected about 141,000 square foot of wall area. Again, Florida, a lot nicer weather than what we see here in the Midwest. So winter conditions really don't play a role there. Appleton, it's one of the first schools ever done with insulated concrete forms. They did switch because it was a winter build. And it did save them about $50,000 in winter heat charges. So again, that was a driving force for them, is to build through that winter construction season and try to save as much money as possible. When we start looking at codes and specifications, we are really looking at what we call the ASTM E2634. That's the labeling in red. That is for flat wall insulated concrete forms. And maybe 8 years ago, 9 years ago, if we were to send over a CSI spec list or a 3-part spec, we would have probably 15 or 20 documents associated with that. When this standard came out, it really consolidated and put it into one folder. So any flat wall ICF manufacturer is going to have an ASTM E2634. And that's really going to be the governing body in there. And with that, you're going to have an ICC evaluation report or maybe an IRR report. Again, Miami-Dade, I know we're not close to Florida, but Wisconsin has a code approval process. We'll look at that as the standard. And when we get into building codes for ICF, I just want you to please think about the simple fact that it's concrete. It's not unique. It's not some magic product that's unique to the approach. At the end of the day, you're dealing with a reinforced concrete wall. So whenever applying the codes to that, let's think about a monolithic cast-in-place concrete wall. Again, the construction type will determine the ICF section, whether it's non-combustible construction, type 4 construction, things like that. It's really going to drive on what you need here. So again, as a recap, flexible core thickness, 4, 6, 8, 10, 12. We have the ability, and other manufacturers have the ability, to get up to that 24-inch, 30-inch wall cavity. So if you had something very specific, maybe an underground facility that's 12 or 14 feet below the ground surface, you might have a thicker wall. So we have that capability. Below grade, again, single story, curtain walls, multi-story. Here's a dorm, again, higher education, but still ties in with the educational facility. As a recap for floor and roof options, Hambro, composite deck, hollow core, it really doesn't matter. It's your choice to choose how you want that to tie in. We worked with them all. It's a simple detail. We just make the adjustments and move forward. So it might be driven by availability of just resources in your local community or price alone. So there are different decking systems, and we're capable of working with any of them. As you think about your design process and what you need to have out of that form assembly, years ago, it was pretty much just a standard and a quarter. Now you have the 90s, the 45s, a brick ledge form. You can do a double brick ledge, T-form units, radius cuts. Most manufacturers today offer some kind of this availability. Not all of them do. radius forms, but some do. So as you get into green or LEED certifications, you get into core and shell or new school, ICFs alone in general will get you about 35 to 37 points of LEED accreditation just by using insulated concrete forms. So about the only division we don't touch in there is water. So again, LEED, not a lot of people really go for the plaque, but most people seem to design to that standard. This concludes. I do want to apologize. My phone was blowing up. It probably gave you guys some feedback in the background. You know, we'll open it to questions now at this time. I don't know, Vicki, do you have any questions from the audience?
I do. Yes, great presentation. Appreciate that, Justice. You guys can still submit questions through the questions pane as we continue to go through those that have already been submitted. So we will go ahead and get started. Have you used self-consolidating concrete with the ICF to avoid vibrating?
We have used self-consolidating concrete. I still like to throw a vibrator down in there just a little bit. But again, as I said before, when we look at wetter concrete like a 7 or an 8-inch slump, we're not going to do the lift heights that we talked about of 4 foot. It might reduce it down to 2-foot lift height. But again, what we'll do is we'll factor in how far we can pour before we've got to get back to that starting point. But yes, self-consolidating concrete has been done hundreds of times, especially in heavy rebar cages. Yes.
All right. Do you have any recommendations for insects tunneling in the insulation?
So we do. We offer we call it Preventol. It comes from Georgia, and it's got a chemical in there to deter, I'm going to say, rodents and mice and termites. Again, you're still going to treat the ground outside the facility, but it's a product called Preventol, and it can be impregnated right into the EPS bead for below grade applications and above grade if you choose.
All right. Do you have any details for thickened edge or a frost-free footing? That's a tough one.
It is. So monolithic slab, absolutely. If you want to, as an example, go 18 inches down, 18 inches thick, there are products out there. We can have that conversation on how to protect that from frost, and how do we meet code with that as well. We do have that ability, and we can provide that detail. So.
All right. We'll keep on going here. These questions are just rolling right in, so which is great. Is the wall bracing a purchase only, or is rental available?
So I'm not supposed to plug anybody, but I've got to plug Stetson. They're the distributor in this market. Stetson, Brock White, the CSG family has hundreds and hundreds and hundreds of sets of bracing available to them, both 10 foot, 12 foot, or even tall wall. So most distributors that represent an ICF manufacturer should have bracing. If you get into a school and the distributor doesn't have bracing, most of our national installers, or even here in the Midwest, they own tall wall bracing. Some have 600 sets, some have 300 sets. So not an issue. It's not a purchase required by a school district or an ownership group. If the installer doesn't have it, our distributors have it.
Are the costs per square foot you reference adjusted to 2021 or the year of construction?
So I'll talk about this. If this was not an AIA, I'd have a slide deck for that. I'm going to give you an example of the Graceland and Hollibird School out in Baltimore. Back when we designed that school, we gave a prelim budget at 65% of the drawings, and we released that to the architect and the school board. 6 months later, when the bids came in, we were actually 2 cents higher than the winning bid. We are not volatile. We're volatile in terms of pennies per pound for insulation, like plastics. But the volatility you're seeing in today doesn't really impact us too much. Where we might see that impact is fuel surcharges, You know, when we get concrete, if diesel was to shoot up to $4 or $5, it's going to impact that a little bit. But percentage-wise, marginal, very marginal. In most of our projects that are even being built today, they are right on budget. They have not been hit by that. And the best person to reach out to would be your local ready mix association or the Iowa ready mix to have that conversation. But if we are not hitting budget, that's usually the driver is concrete, but it's pretty stable at this point.
All right, there is another question as it relates to some of the costs listed for the various schools. Does that include the cost of the solar panel installation?
So the Richardsville School at 206 did include the photos on top. The example being, if that was just a code compliant school built to just code compliant standard, Kenny Stanfield had said that the solar package would be $9 million to run and operate that school at net zero. When they used ICF, some geothermal, some day lighting, the kitchen is a steam kitchen, it's not fryers. That solar package went down to $2 million. So yes, that price does include the turnkey number with the solar included.
All right. With concrete being a large contributor to greenhouse gases, how is the relationship between ICF and concrete addressing them?
So I'm an expert in ICFs. What they're doing on the National Ready Mix Association website, go check it out. They're adding carbon to their concrete. They're doing a lot of things, and I'm not the expert there. But think about if I build a project and it lasts 50 years with cavity wall systems. It may last 200 years with me. I'm building it one time for 3 generations. They're repairing stuff every generation. So sustainability is a big impact there. You know, with some of the fibers out there, reinforcing mechanisms, can we get a thinner wall assembly? Can we reduce any of that? You know, there's always a play there. I understand your concern. The best people to answer that is going to be Iowa Ready Mix, Nebraska Ready Mix, and the NRMCA. And they would love to have that conversation with any one of you.
Okay. We are going to pop back to the dollars per square foot question. So the question was, you show dollars per square foot from a decade ago. That would be much higher now, correct?
So, you know, it's probably going to be impacted, but I'm going to say yes, but I'm not going to say at the magnitude of what you think it might be. An example is in 2012, an ICF 8-inch, 10-inch concrete wall was running right around $17 a square foot for 8-inch. Today, it's running right around $17.75 a square foot for 8-inch. So, you know, floor space, FF&E, finished fixtures, equipment, that may have gone up. But as far as the building envelope, the integrity of the ICF package, you're talking less than, you know, 3 or 4% increase. So it's been pretty stable.
All right. Are mechanical systems often downsized when using ICFs when compared to other construction methods? And if so, are there first cost savings to be had?
There is absolutely first cost savings. A couple of the things that you're going to think about is, as I start to look at that unit on top of the roof, and if I can reduce my energy needs by 40 or 50%, I'm going to downsize that unit as well. I'm going to downsize all of the electrical poles that are required to get to that panel or that rooftop unit. Take Richardsville as an example. If I can back up here a little bit, I had said that they did a number of things to reduce and get down to that 18.5 EUI. That was geothermal, that was day lighting, a lot less cables in there. It's all wireless, and ICF. So they took a holistic approach. It wasn't, I'm not going to lie to you and say that it was ICFs that got them there. It was not. It was the driving force to get them in the correct direction. And for geothermal, the example that Kenny uses, if I needed 200 wells to get to net zero, I'd only need 100 if I used ICF. And as I start to look at glazing and daylighting, by doing that, I could have reduced another unit of measure and another unit of measure. So it's a holistic approach, but the building envelope, the roof envelope is the starter. That's the driving indicator there.
All right, we've got some great questions still coming in, and we still got some time, so we'll just continue to get through these here. Let's see, where did we leave off? Who does the engineering of the walls?
So most of your structural engineers work every day with cast in place concrete walls. It's not new to them. Again, I kind of mentioned that. I don't want people to fear it, because all we are is a form. We're a form first. After that concrete's placed, we're now insulation and furring strips. So again, concrete is concrete. They use it every day. Your engineer, your structural engineer, part of your design team is very, very capable of doing that. If not, if they're not comfortable, we can work with either our team, the NRMCA, Iowa Ready Mix, somebody can point them in the right direction and answer a lot of questions and get them down the correct path.
All right. Question about approved installers. How many are there many approved installers in Nebraska?
So yeah, there's actually a school getting ready to come out to bid. It might be out currently. Last year, there was another school in Omaha, and I think they had 4 or 5 bidders on a national scale bid that. So you have a number of skilled installers in Nebraska. Plus, you're actually going to have 4 or 5 other Midwest regional installers coming to bid that. Likewise with Iowa. If something was to happen in Iowa or Minnesota, you would feel comfortable knowing that you're going to have about 6, 7, 8 installers bidding on that on bid day to any general contractor. So,
all right.
And
is there ever a need
qualified? So.
Perfect. On top of that, how do you become a certified installer?
Well, let me first say it's really not certified. I should say it's qualified. In our process, we never want to submit to an architect a residential installer for a commercial grade application. These installers would first cut their teeth in residential construction and then light commercial and work their way up to that. And one way to do that is as a manufacturer, we'll work with them. We'll teach them the trades, and we'll get them started on smaller profiles. Then we'll get them into larger, and then again, school, med, fed, and ed. And then we have an installers list that we would provide to any architect as part of that. And inside our specifications, we have a requirement there on the performance and the ICF installer qualifications. So we do cover that, and we're very adamant about that as well.
Great. Is there ever a need for a protection board for backfill? And if so, what is used?
So yeah, take Minnesota as an example. About 4 years ago, 5 years ago, they require what they call a slip sheet or a protection board in between the earth and our waterproofing. So if you were to get into tough and dry, a watchdog, an application, H3, you're going to spray that wall, and then they're going to put on a warm and dry board. And that's going to be 1, a drainage mat, and 2, you can have earth up against it. So that is that protection board against that waterproofing. Here, if you use the rolled rubber, our good products of, what are they, 3 foot by 60 foot roll, 60 mil, you're gonna put on maybe a 1/2 inch or a 1 inch dowel sheet of styrofoam just to protect that. We wanna keep the silt away, number one. We wanna keep stones away. We just don't want anything rubbing through and hitting that, so.
All right. We still have some great questions. We may not have time to get to them all. I will drop at least 2 more here for you before we wrap up. And then if we did not get to your question, Justice will definitely follow up with you personally. But definitely has had some wonderful questions coming in today. How do you handle non-standard angles such as a 30-degree corner angle?
Sure. 30 degree, 60 degree, 120 degree, we field cut those. Yeah, most installers are going to have what I call a whaler or a piano hinge whaler. They'll mark that on the footing. Let's say it's 120 degree angle. They'll have specific bracing to lock that in and hold that profile at that degree. So it's field cut with EPS, and then it's reinforced with strapping and maybe some glass rod to hold that there. But again, it's just simple field cuts in the field.
All right. Do these forms meet NFPA 285 for combustible materials, and are they tested assemblies?
So we're working through that now. A lot of that's going to come down to the cladding. Say you have an air space in between your brick and the ICF wall. Our concrete does meet that, but we have the plastic insulation. What we would try to do is return that brick veneer to a window or a door head. As we put in that lintel steel to support that brick veneer, sometimes what we have done is taken that steel back to the face of the EPS or the concrete so that we don't have a chimney effect coming through there. So to say that we have an NFPA 285 as an individual company, we're working on it. We're not there yet. We have some applications, but it's still going to come down to each type of cladding system, whether that's an eaves, a brick. Each one is going to be different on how we detail around that window. So to answer your question, no, we'll get there. But if you have a project and you have a system for the cladding, it's not that we don't have a workaround. We'll just design to your need based on that one.
All right. And the final one for the day is the ties are full width of the wall. How watertight are the ties?
So the ties are actually about 5/8 of an inch below the EPS. So they are below that. It is plastic. It is EPS. Concrete is your WRB. Now, if we get into class 1 construction or you want to put a WRB on over top of that EPS, then we would spray a fluid applied barrier over top of that. Then we really wouldn't have to worry about that. If you're not going to use that, you know, they could translate back all the way through the water assembly, but you're going to have an air barrier and a moisture barrier, one with the EPS, and then again the concrete. So I don't see water standing anywhere in that wall assembly. Gravity is going to pull it down. So we would treat that, you know, at that ground level as well. So for a little more clarification, if you want something there, send me an email and I can get some answers back to you. Just to make sure I understand the question, but to provide you the correct information back to your question.
And Justice does receive a full list of all of these questions, even those that we did answer today. And as I stated earlier, if you did ask a question and we were not able to address it or we didn't have time to get to it, Justice will definitely be reaching out to you to get your questions answered. So I'd like to thank Justice and Nudura for providing today's wonderful webinar. Thank you to all of our attendees for joining as well. In the next few days, you can expect your AIA credit to appear and a certificate of attendance will be emailed to you. Once you exit today's webinar, you will receive a brief survey on the presentation. We would appreciate it if you would complete that and provide your feedback. Today's webinar was also recorded, and you will also receive a link to view today's presentation. On behalf of Construction Supply Group, Whitecap, and Nudura, thank you for joining us today and enjoy the rest of your day.